Welcome back to the shop and to the channel. Well, on the last video, I made a set of plastic gears. I decided to mount them on this piece of plate, although I set the center dimension wrong, so they bind up. But I had so much fun, I decided I want to make some gears out of steel. So I happen to have these two pieces of scrap that was in the scrap bin, and I think they'll do nicely as blanks for some steel gears. But instead of making straight spur gears, I think I'm going to try my hand at cutting a helical gear. So these are a little bit oversized for what I need. So the first thing I need to do, I want to take them over to the lathe and machine them down to be a more appropriate size for the gears I want to make. First things being first, I want to face off each side of the gear blanks. I've got the forejaw already in the lathe, so I'm just going to take advantage of it. It'll sit flat enough on the top of these jaws to where I'll have room to go ahead and take a few thousandths off of each side. The blanks already had a hole drilled through them, but I don't know how concentric they are with the OD, so I've got a gauge pin that's roughly the same size. In the drill chuck here, I'm hanging the blank off, and that'll at least help me get this thing at least dialed in a little bit. I'm more interested in the bore being concentric to the spindle than I am the OD. I've got to turn down the OD anyway. Yeah, that's going to be concentric enough, at least for now. Right now, I just want to face these off and make the thickness between the two blanks consistent. I'm only going to do this one face right now. I'm going to swap this out for the other one. I've got this blank now flipped over so that the finished side is against the jaws. And I am going to dial this bore in now. I want to try to get this as concentric as possible because I am going to bore this out just a little bit so it can fit on a arbor that I will eventually be making. I was originally going to bore this out with my small boring bar, but then I couldn't figure out what I did with it. So it is somewhere in the shop. It just, I can't find it. So I am going to end up drilling this out, which will be fine. But having this on center with the tailstock is going to be a little more advantageous than with it not being. So I've got my I got a dial indicator here with one of these right angle attachments. These are kind of slick, and we'll get this dialed in so I can bore out this hole. Before I bore out this center hole, I'll face this side and get it cleaned up, get it set to a consistent width. When I go to turn the outside diameter of this blank, and then also when I set it up in the horizontal mill to machine the gear teeth, I'm going to mount it on an arbor. And I'm going to make a good hefty arbor that's hopefully not going to flex much. And as such, I want to put a spigot on the end of it that's, at least a reasonable size. So I picked 9/16. Partly because I have some 9/16 inch nuts, and it'll be easy for me to thread that, at least on the end of the spigot for that arbor. So I've got a taper shank drill here. We'll drill out this bore to 9/16 inch so it's ready to be mounted on the arbor. I'll do the same thing to the other blank. Well, I have the blanks, at least the faces, and this bore machined to approximate size. Next step here, I've got this piece of material, again, pulled it out of the scrap bin, that I'll be using to make the arbor. I've got the 6-jaw now mounted on the lathe. We'll get this piece of material mounted up. I'm going to mount up this partially turned side first, just so I can clean up the rest of it with some emery. I just wanted to clean it up, get rid of some of that surface rust. I'll flip it over now and start machining the spigot. I was getting ready to face this off, and this piece of material just doesn't seem to be turning very concentric. I'm going to pull it out of here, and I'm going to wipe down the inside of the jaws just to see, make sure that there's nothing on there that would cause this to be out of concentricity with the spindle. The 6 jaw is pretty accurate. Yeah, that didn't really help much. So I think when I first adjusted this chuck, because it is a true adjust chuck, I used a smaller piece of material. Using this larger piece probably needs a little bit of adjustment. That's one thing I really love about this little 6-inch chuck is I can dial it in. So I'll get some Allen keys and a dial test indicator here set up on the semi-clean section of the shaft and try to get this running concentric to the spindle. That's not perfect, but it's a lot better than what it was. So there's still probably a little bit of pitting or surface rust on this piece of material, so I don't expect it to be perfect, but that's within 1/1000th of an inch, and that'll work just fine for what I need. Well, that's turning a lot more concentric than what it was. So now I can go ahead and face this off, and I'll turn down a portion of the end of it to be about 9/16ths of an inch in diameter. Well, that last pass looked horrible. I suspect I chipped this insert, so let me swap that out and try again. That's definitely an improvement in finish quality, but I did have to take a little bit more off than I wanted to, so this fit on the blank is a little bit sloppier than I would like. Well, sloppy or not, it is what it is. So now I need to thread the end of this for a nut. I'll start by putting a nice healthy chamfer on the end. I do not have a die of this size and pitch, so I'm going to single point thread this. I'm going to start here with my threading tool by creating a thread relief a little bit deeper than what I need the threads. Just kind of widening out a little area here on the end of this spigot, so I have a spot to stop the threading tool. Put a black Sharpie here on the end so I can run a scratch pass. Well, that's right at 12 TPI, so got everything set up correctly. So now I'll just start threading this. I'll feed in 10/1000ths of an inch at first. Put a little anchor loop here to do the threading. I've thinned this out with a little bit of water just to make it flow a little bit better. Not quite ready to go all the way on, so we'll take a few more passes. Well, that's a nice fit here on the nut. A little tight at the end. Might be some junk in the threads, but that's okay. I'm not going to be threading this on that far. I do think that even if I did have a 9/16 12 die, that single point threading probably was easier to do than using the die. Well, I'll get the first blank here mounted on the arbor and tighten this nut down so I can finish the OD on the blank. I intend to make a 56 tooth gear, and as such, my OD on the gear should be 3.625 inches, 3 inches and 5/8, which is wrong because I am going to make a helical gear, and helical gears use different formula. So what you see me doing here is the first step of me making some mistakes that ended up creating some problems. As Adam Savage says from Mythbusters, failure is always an option. I do recover from it, so stay tuned. But yeah, setting this gear up at this size is going to end up creating problems for me that I compound later on. With this gear now, what I think is the right size, I'm going to go ahead and chamfer, do a nice heavy chamfer on both sides, both edges. With this blank finished, I'll do the same operation on the second one. Well, here are the two gear blanks. I opted just to leave the second one on the arbor because it's going to go into the dividing head on the horizontal milling machine. Now, originally I was just going to cut some straight spur gears, but since I've decided to cut these as helical gears, I need to do some changes to the setup on the horizontal mill. Well, if I had a universal table on this mill, I would not need to do what I'm about to do next, which is to remove this arbor and the gear cutter from the main spindle. When you're cutting a helical gear, you have to orient the gear cutter at an angle in relationship to the gear blank. And you can do that in one of two ways. The way that folks like Keith Rucker and others you might see have done it is to just pivot the table, because their table will pivot. Mine does not. What I lack in having a universal swiveling table, I have an abundance of a universal milling head. If this machine had a universal table, I could just pivot the entire table to my helix angle, which I'm picking as 15 degrees, not because I need a 15-degree gear. It's just a number that I picked. But I can orient the table so it is moving 15 degrees in relationship to the spindle. What I need to do is orient the spindle to be 15 degrees to the table, and that's why I'm using the universal head. First thing is I got to mount the drive gear that was so graciously manufactured and given to me by Tom Stover at Tom's Rabbit Hole. I did have an earlier one, if those of you remember, that another friend of mine, Cooper from Cooped Up in the Shop, he made for me. That one was sort of thrown together, gear hobbed, and it didn't work out all that great. But this one here that Tom made me is absolutely perfect. So I'll get that mounted in the spindle, and we'll swing over the universal head and get it mounted on the front of the machine. The parking attachment here on the machine with the crane certainly does make storing this universal head a lot more convenient. It makes it a lot easier to move it into position, but it doesn't make it any easier really to get it lined up on the front of the machine. It does take a little bit of finagling to get this mounted on the dovetails to the front of the machine, and then to get the overarms lined up with the mounting bracket. It's just a bit of a constant back and forth in getting the gear on the spindle, the drive gear, lined up with the gear that's inside the universal head, and then getting it, at the right height using the parking or the crane, and getting these overarms to slide into that clamp that's on the back end of the universal head. It's not extremely difficult because I don't have to hold it up, but it isn't really easy either. Sometimes you have to kind of jiggle it and get it just in the right position for it to slide into place. Well, I have both overarms now are all the way into that drive bracket, so I can tighten down the clamping nuts on the top. Well, that's only part of it. Now I need to tighten up these clamps for the dovetail. Need to make this thing super tight. The tighter it is, the more rigid it will be, and hopefully the better surface finishes I will get. Now I'm going to loosen these 4 nuts on the swivel bracket so I can bring the spindle of the universal head down so it is parallel with the travel of the table. Now loosen these 4 nuts on the front of the milling head so I can rotate it and pivot it so it's 15 degrees offset from the table. Well, putting the arbor now into the spindle of the universal head, I've noticed a couple of problems. One of which is it's a little hard to reach the nut on the back of the drawbar, but more importantly, because this arbor is sitting in this 1-inch tool holder, it's pushing it out away from the spindle quite a bit. And even with the table, the saddle rather, all the way forward, there's there's no room here. The gear blank is not going to pass underneath the milling cutter, so I have to think of something else. Well, I've thought of an alternative that I'm hoping will work, and that is to pivot this milling head 180 degrees from the orientation it is now. And you might be thinking, well, if I spin it all the way around, it's going to just hit the base of the machine. But this universal head has an interesting feature that you don't find on some variations of this. Well, this nut, this little clamp here that's on the front of the overarm bracket, allows me to separate the drive bracket from the overarm bracket. And what this will let me do is pull this whole universal head out forward from the base of the machine. There is a spline shaft that rides up through the middle of it that drives the spindle. It doesn't have to be directly attached to the front of the machine. And it's a little bit tricky. Again, some alignment issues make this a bit of a challenge, but with everything loosened up and the parking attachment crane out of the way, I can get this thing moved forward. That took a little bit of effort, but now that I have everything pulled out and tightened back down, I'll remount the arbor and we'll check to see if we have clearance. From this angle, it looks like I will have enough travel on the table for it to meet the cutter. Let me get it remounted up and just make sure. When I mounted the gear cutter on the arbor, I did move it so it's a little bit closer to the spindle. I think that will help, obviously, with a little bit of rigidity, but also help me with making sure that I can get it underneath the center of the arbor that'll be in the dividing head. And this time I'll actually tighten the nut on the arbor. I thought I tightened it good enough when I cut the straight gears, but apparently I didn't. Some viewers noticed that nut here that I'm tightening now actually came loose while I was making those plastic gears. I got lucky that it didn't create a bigger problem. I've got the other arbor that I used on the plastic gears. I'm going to mount that in the dividing head just to see if I'm going to have the right amount of travel in the table to reach the center of this arbor. Well, that looks like it will just barely reach over the center of the arbor, which will be where the gear blank is. Kind of a funky little setup here. I wasn't expecting that this was going to be the case, but I think eventually I'm going to have to build another arbor because obviously this one is borrowed, as I mentioned before. in the last video from Tom at Tom's Rabbit Hole. I'm going to have to make my own, and I think when I do, I might forego the use of the tool holder and maybe machine either a custom 40 taper tool holder for a 22 millimeter arbor, or maybe even get an NMTB 40 ER32 or an ER40 collet tool holder and use a 22 millimeter collet to hold my gear cutting arbor. Well, in any case, I do have a setup that will work for me, but before I can use it, I need to do a little bit of measuring and setup on the new gear blanks to make sure that they are aligned exactly where they need to be. Well, to help me make sure that this gear blank and the gear cutter are aligned perfectly on the machine, I need to do a little bit of layout here on the gear blank. With a little bit of Sharpie here on the edge of the gear blank, I'm going to use a machinist square here to scribe a vertical square line. Next thing I need to do is I'm going to use my height gauge here to scribe a line directly down the center of the width of the gear blank. I'm zeroing it out here on the top of my grade A granite surface plate. I got a little 12 by 18 inch granite plate that I have on a utility cart. I will measure the height of it with the height gauge, divide that by 2, and then scribe a horizontal line. With those two lines marked, I want to make sure that I can find the intersection of them. So I've got it in my vise, and I'm just going to take a center punch here. And I'm going to find the intersection of those two lines and just punch a little small divot. Well, I'm getting a little bit sidetracked here, but I want to see, do I have my DRDRO set up correctly to cut a helical gear with a 15-degree helix angle. So I put a Sharpie on the end of an articulating indicator arm. And I have the DRO set up for what I think is the correct lead length. And I will say that this is completely wrong. The lead length that I have calculated is wrong. So forget that this is the wrong angle, but what you're seeing here I think is kind of cool. Is you can see how the dividing head is moving in relationship to the table. And I'm able to even move to the next gear location. And as I power feed across, the gear blank, the Sharpie is marking the path that the gear cutter will take, which is on an angle. I just wanted to kind of see if this was set up correctly, and I wish I would have taken a little bit of time to do some inspection of these lines, because I might have realized that this is wrong. This is going to cut at the wrong angle. Well, I don't know that all that setup is wrong yet. There's actually quite a few things I've done wrong. And that will become obvious a little bit later in the video. But right now, I need to find the top of the gear blank, and I'm using my height gauge to do that. With the height gauge now zeroed, I need to lower it half the diameter of the gear blank. Now this sets the height gauge to be exactly in the center of the gear. So now I want to locate that little divot that we made. The blue Sharpie got rubbed off, so now it's got a little bit of red Sharpie over it. Might be a little bit difficult to see, but I rotated the dividing head so that it's perfectly in line with that dot and the height gauge. Now, if I rotate the gear blank now 90 degrees up, that dot will now be exactly at top dead center of the gear blank. I'm going to do something similar here with the gear cutter. I'm going to set the height gauge to be at the very top of the top tooth on the gear cutter. I'm going to zero it and then lower the height gauge exactly half the diameter of the cutter. With the spindle in neutral, I'm rotating this gear cutter so that one edge of one tooth is exactly in line with the height gauge. Well, just like we did with the gear blank, we've got this height gauge now set up exactly in the center of the gear cutter. I don't need to rotate the gear cutter, but what I do know is that tooth that's on the bottom, the very tip of it is going to be exactly in the center of the rotation of the spindle. Well, let me move the gear blank now over underneath the cutter, and hopefully what I've been doing here will start to make sense. Well, with that little dot on the gear blank being exactly at top dead center, and that bottom tooth on the gear cutter being exactly at bottom dead center, if I line up the tip of that tooth with that dot, then I will know that my table is perfectly aligned with this gear cutter. I won't have to do any kind of test cuts and guess or try to do it visually other than lining up the tip of that tooth with that little divot in the gear blank. Well, I guess I'm about ready to start cutting a gear. So I do have the gear lined up, but I want to touch off so I can zero the vertical axis. I have chosen to climb mill this just to keep any chips and stuff away from the dividing head. This is going to be a pretty shallow cut, so I'm going to do this first little one here without any oil. Well, that first cut does not look great. It actually looks too wide considering the size of the gear cutter. Now, I know what the problem is now, but while I was doing this, I really wasn't sure. So I started to speculate. So the first problem I noticed is that there was a lot of backlash here in the dividing head between the worm drive and the chuck. And I was actually kind of surprised that there was this much backlash in it. So there's an adjustment on the side of the dividing head for engaging the worm drive in the spindle of the dividing head. So the first thing I'm going to do is try to adjust that and get it a little bit tighter. Well, that's definitely a little bit better in the backlash area, but I do find that if I tighten it down too much, that it actually ends up acting as a spindle break on the dividing head, so I can't eliminate 100% of the backlash. There's going to end up being some. Well, I think I've eliminated as much as I can here. I am running this pretty slow as far as RPM based on some data I got from a speeds and feeds calculator. But what I've noticed with this machine, and I've noticed it before, that when I am power feeding from left to right, that oftentimes the table wants to stall. And I'm not exactly sure what causes that, but the table feed will stall. I think there's an issue in the clutches with the power feed. But I find that if I feed the table from right to left, that I have fewer issues with it, or actually none at all. It's only when the table is feeding from left to right that I see this. But I am kind of going for broke here, and I'm going to start making some cuts around the outside of this gear blank. This is the first time I've ever done anything like this, so I don't know yet that what I'm doing is wrong. Well, I'm still experiencing some backlash here in the dividing head, and so what I'm kind of doing to accommodate that is I'm just putting some drag on it. I'm essentially holding on to the dividing head while it's moving and taking out the backlash manually. Now, I know there are better ways to do this, which would be lowering the work, moving it underneath the cutter, then raising the work back up. But I was kind of hoping I would avoid having to do that. Because of the way that this whole gear train works, my electronic low lead attachment, for lack of a better term, there's zero backlash in that particular configuration between the table travel and the rotation of the dividing head. Where your traditional low lead attachment is dependent on the motion of the lead screw, if there's any backlash in the lead screw, your dividing head won't rotate in time with the table movement because the lead screw will be moving before the table starts. And to compensate for that, you would lower the work, move it out of the way to the other side of the cutter, raise it back up, and start your cut again. My hope is I will not have to do that with this setup. But my limitation is the backlash that's in the dividing head. And what I'm doing here, I think, is solving a problem. But what, again, I don't know yet is I've got other problems that I haven't realized. One change I am making is I decided to mill in the other direction, so I'm doing conventional milling. Right now I am backing up to the start position, using my finger there to take out the backlash, rotating to the next gear position, and then feeding from right to left to make the cut. I'm probably taking about 25 thousandths here, I believe, per pass. I am being pretty conservative on my depth of cut here because I'm not sure what to expect. So my depth of cut here has only been about 25 thousandths per pass. And I am still milling, conventional, and then using my hand on the chuck to take out the backlash. And it's starting to look like a gear, but, I don't know that it really looks like the gear I'm expecting it to be. Well, and it's kind of right about here that I just realized this thing is looking like crap. It doesn't look like it should look, and I'm not sure what is wrong with my setup. Either I've miscalculated something or the setup is wrong. It feels fairly rigid. My feeds and speeds don't feel like they're too egregious for the depth of cut, but when you look at this gear, it's just garbage. There's inconsistency in the width of the tooth. The valleys between the teeth are just, they just don't look good. And I'm thinking that is partially related to the feeds and speeds. I think I can improve on that, but the tooth profile, it's just wrong. I decided to go ahead and take the gear blank off of the arbor because this thing's trashed anyway. I know this video is not all that great, but I'm sitting there trying to highlight the edge of the tooth with the Sharpie. And there's spots here in which it is like almost a razor thin, almost like I skipped a hole in the dividing head and missed it. But I know that's not the case. So it's definitely got to be something else. I shared some photos of the gear with some friends, including Stefano, who invented DRDRO, and just asking for some advice. And I did get some. And, I was thinking maybe that this was a cumulative math issue inside of DRDRO. Stefano assured me that it likely wasn't, and I did some experimenting with the other gear blank and a Sharpie marker, and sure enough, that thing was flawless every single time. So there was definitely something else going on here that I haven't detected. I went ahead and looked back at the lead length that I had programmed into DRDRO for this helical gear and realized my calculations were completely off. And this angle of these teeth is not correct for a 15-degree angle. And what that essentially means is this gear blank was rotating at the wrong speed. It should have been rotating slower than it was. And because it was rotating faster than it should have been, that's what caused the valley between each of these teeth to be so much wider than it should be. I also shared photos of this in my gear calculations with Tom, and he told me that my calculations were even worse than I thought. First of all, for a 56-tooth gear, this gear blank is too small. It should be bigger than it is. Well, I can't make this blank any bigger, but I can make it smaller and start over. And so that's what I did, is I built this gear calculator for calculating the dimensions of helical or spur gears and decided on a 52-tooth gear because I can machine this blank down small enough to get me there. So that's what I'm going to do. I'm going to reprogram the DRO for the correct lead length and machine this blank down to the correct size and start over. Well, off camera, I went ahead and machined this blank down to be a smaller size and started just doing a touch off of every tooth all the way around. I got some different feeds and speeds from Tom. He suggested I speed up the spindle but slow down the feed. And right now, all I'm doing is I'm trying to get just a 5,000ths, I guess, scratch pass of each tooth. This is going to take a little bit of time because it takes about 3 minutes to do this for every tooth, but I can already tell by looking at the marks that the gear cutter is making in the blank that I am much better positioned than I was before. It's not as wide as it was. This is definitely turning at a better rate than what that first attempt was. So I feel like this is a bit promising. I still have that backlash issue in the dividing head, although I have eliminated almost all of it. And I don't think it's going to be a major issue for me going forward. We'll find out when this gear is finished, but I think we're on the right path anyway. Well, I'm starting to cut some deeper gear teeth. I cut one of the spaces here at 90 thousandths depth of cut. The final depth of cut is 135 thousandths roughly. Tom assures me that I can take the full depth of cut in a single pass. He said, what's the worst that could happen? I suppose it could go pretty catastrophic, but it wouldn't be the end of the world. So I am going to go ahead and raise the knee up to the full depth of 135 thousandths and recut this first tooth. It shouldn't have any problem. But then each tooth after that is going to get one pass, full depth of cut. Cross your fingers. Well, I started cutting the second tooth. This is a full depth of cut, 135 thousandths. I've got the machine running at 262 RPM, and the feed rate is 1/2 inch per minute. So this is going to take about 3 minutes per tooth, which translates into almost 3 hours to cut all 56 teeth. Why in the world did I choose 56 teeth as my first ever helical gear? I don't know, but here I am. It sounds a little crunchy, but the chips are very small. It's not bogging down at all. I've got plenty of oil lubricant flowing down the cutter. The speed is nice and slow, so it shouldn't have any problems clearing the chips. Took a look at a speeds calculator, and this should have no issue. The chip clearance is right on target. So we'll just keep cutting gear teeth. It's going to take a little while. About 3 hours. It'll take a little while. I'm still compensating for the backlash in the worm here by putting some drag on the chuck, and I'm speeding up the reverse feed on each tooth. It does sound a little bit like it's taking some material off on the back feed, but I don't think that's a major issue. I'm going to try to speed up the spindle here a little bit to about 320 RPM. Tom told me somewhere around 300 RPM will be good, but I ended up backing this back down to the 260 only because at this speed it was really flinging a lot more oil than I really wanted it to. Well, so far, these first few teeth look outstanding. They look way better than that first attempt. Getting a little bit of a burr on the back end, but that's expected. The tooth appearance, the thickness on the top of the tooth looks like it's consistent, at least by eye. I'll know more when I get it cleaned up, but I think for now, I'm just going to keep sending this one tooth at a time. Well, this is the final pass here for all 52 teeth. And I will say, up to this point, there have been absolutely zero hiccups with this second iteration of the gear. I've been, really happy. It has taken quite a while. I did take a break about halfway through for some dinner, but then came back out and picked up exactly where I left off. Really happy with how this looks. I'm hoping that once I get it off of the arbor, it looks as good cleaned up as it does right now. Well, I got a little bit of cleanup here to do on this gear, but I can no longer call it a blank because it is definitely a gear. How good of a gear, I don't know yet. We'll know when I get it a little cleaner. We'll get the oil cleanup off of it. I think I will take it over to the lathe and use a file to file down those burrs. Be a little bit easier to do that with it running in the spindle of the lathe. I'll do that off camera and bring you back once I get it cleaned up. Well, if it looks like a duck and walks like a duck and talks like a duck, it must be a duck. And this must be a helical gear because, boy, it looks so much like one. I really can't complain about anything with this gear. The teeth on it look really clean. The valleys look fine. Really, really happy with the tooth profile. Yeah, I don't know, to be honest with you, if it is a perfect gear or not. Um, the only way to check it is with a mating gear, and I don't have one of those yet, but I do have a gear blank. This was the other gear blank I had attempted. This is actually the first one. The one I just finished cutting was the second gear blank. I just turned that one down to the right size. So I'll come back and do the same for this one. This one has enough room that I should be able to machine it down to the right size for a 52 tooth gear. But yeah, I'm really happy with how this turned out. If I take a protractor that's set to 15 degrees on this first failed gear, you can see that these gear teeth aren't even close to being 15 degrees. And that's all because I programmed the lead angle to be wrong. And it's still going to cut the gear tooth, but it's going to end up making that valley wider. If I look at this gear, yeah, that's about 15 degrees. It might not be perfect. It could be, how I'm holding the protractor might make it look like it's a little bit off, but no, I think it's pretty good. This one right here, the angles are they're just wrong. Well, before I end this video, I think it's incumbent upon me to kind of share what the setup is in the DRDRO in order to get the results that I finally ended up with. As a refresher, I'll step back here into the setup for the servo. The gearing ratios are specific to my specific situation. It has to do with the specs on the servo motor itself, how I have the servo driver enabled, the pulleys, the dividing head, all that calculates out to that number. The speeds, that's again specific to your situation here, and they're just kind of what you want. I didn't want this thing to be accelerating or moving too fast, so I kind of reduced these numbers just to give it a little bit less acceleration, so the dividing head wasn't spinning too fast. I'm going to reset some of these values here. So here I'm going to set up for a 52 tooth gear. I can reset my angle on the dividing head so it now thinks it's 0. I'll reset this index to 0, and I've got everything else zeroed out. When I re-indexed the dividing head, it moved it, so now I reset that to 0. Now I want to look at these numbers over here on the right side of each axis where you see num and din, so numerator and denominator. Each axis has its own ratio that corresponds between the movement of the axis and the rotation of the rotary controller. So out of the box, this is set for 360 and 1. And what that means is when I move that axis, if I link the two 1 inch, the rotary controller will rotate the output by 360 degrees. Well, that's going to get that servo moving pretty fast. And that might be impractical for a lot of situations. So especially what I'm doing here, I need to reduce this so that that 360 degree movement is what my lead length is. And my lead length is a lot more than 1 inch. But if I give this a try as it is right now and I go ahead and move the x-axis, I've got the servo disconnected. And you can see that the servo is rotating, even though it's not physically connected. And when I get to 1 inch, or at least close to it, I'm right back to around that 360 degree mark. But if I look at the calculations for my gear, the lead length comes out to 39.449 inches. So what that means is I need the table to move 39.449 inches before the rotary controller will turn the dividing head a full 360 degrees. So now that's where I need to set this numerator and denominator value. So I'm going to come in here and change the denominator to 39.449, but there are no decimal points in this entry. So I can't use that fractional number. I need to do something a little bit different. Well, the easiest thing to do is just to multiply both numbers by 1,000. Because this is a gear ratio, it's not solid degrees. So I'm going to change the numerator to be 360,000 degrees and then change the denominator to 39,449 inches. Now this is a limitation of the UI for the DRDRO. Down inside the guts of this thing, the math still works out the same, whether or not I would have been able to enter a fractional number in here or not. It's just used as a ratio when computing how many pulses to send the servo as it's rotating. Well, I can test this math just by moving the table some distance until the rotary controller shows that I've moved an angle. So I'm going to pick something that's easy to do the math for and just say, let's move the table until the rotary controller thinks that the servo has moved 36 degrees. And if I do 36 degrees, that's 1/10 of a rotation, I should see 3.9449 inches on the table travel. And I'm getting really close to that, which is telling me that the math is correct. And that's really all there is to it. I mean, there could be some improvements to the UI on the DRDRO, but I'm going to take this over having to change gears and shuffle things around and deal with backlash and all the other issues that you have with the purely mechanical solution, not to mention the tedium of rotating a dividing head crank handle. This is just such a fantastic invention. I can't wait to use it more. So I'm glad that I shared some of this stuff with Tom and he convinced me to check my calculations. I do have a link for this gear calculator in the description of the video, but it certainly came in handy. I don't know that this is perfect. I know there are some issues with high helix angles and low tooth counts in which these calculations aren't quite exact, but I don't think I'll be running into too many of those issues. Well, what is this gear going to be used for? Well, that's a bit of a secret that you'll probably find out before the end of 2025. But in the meantime, I think that's going to be it for this video. I had a little bit of frustration, but still I had a lot of fun making this gear. Well, if you liked the video, give it a thumbs up. Subscribe if you're not a subscriber. It costs you nothing. But if you'd like to contribute to the channel in other ways, you can do that through the links in the description, either through PayPal, Patreon, or through channel membership. I hope you enjoyed it. Thanks for watching, and we'll see you on the next one.